here I've listed out the given parts of the problem and what they want you to find. So they give you that the derivative of the function is 1 plus y over x when x does not equal 0, because then the derivative does not exist. They want you to find, for part A, the slope field for negative 2, 0, negative 1, 0, 1, 0, 2, 0, 1, 1, 1, negative 1, negative 1, 1, and negative 1, negative 1. Notice how there's no x values of 0 there because the derivative doesn't exist. And then for part B, they want you to find the particular solution when x equals negative 1 and y equals 1. So for part A, they give you a slope field that looks like this, and they ask you to show the slopes at each of those dots. So what you're going to do is you're going to plug in your x values and your y values into that derivative function that they gave you to find those slopes for the original function. Not for this derivative, but for the original function. Now, something that I like to remember is when you have both variables in your derivative function, then both axes are going to affect what your slope field looks like. Say I only had y in my derivative function, then generally my x value isn't going to affect what my slope field looks like at all, and all of those x values are going to have the same slopes. Say I just had x's in my derivative, then the y values aren't going to affect it, but the x values will. And so here we have both x and y values, so we can see that both axes are going to affect what each slope looks like. Now I'm going to fill in these slopes and you can see what the actual answer is. In the end, this is what your slope field should look like generally. I'm just going to give a point as an example of how I did this. So take negative 2, 0. So the x value is negative 2, so that goes in the denominator, and your y value is 0, and 1 plus 0 just equals 1. So that's going to be negative 1/2 as your slope there, which is what that is. As for grading for the part A, they just want to see that your slopes look like how they should as far as steepness goes, and they want to make sure that they all are different relative to each other. So like negative 1 should be steeper than negative 1/2, and so on. Now this is part B of this problem. So for this part, we're given that the derivative is 1 plus y over x when x does not equal 0, and we also have the point negative 1, 1. So what we want to do is we want to integrate that derivative. So we're going to isolate the 1 plus y and the x and try to get the dy and the dx on each side. So then we get 1 over 1 plus y dy equals 1 over x dx. Then you integrate both sides, and you get ln of the absolute value of 1 plus y equals ln of the absolute value of x plus c. Now you could technically multiply 1 by each side just to show that you did take the derivative of the variable in the problem, but that's not necessary because it's just a derivative of 1. And so then what you want to do is you want to raise both sides to the base of e, and you get the absolute value of 1 plus y equals e to the power of ln of the absolute value of x plus c. Now one thing to point out here is e to the ln cancel each other out, because ln is just log base e, and then you have absolute value of x, so that's just going to result in the absolute value of x, and then your e to the c is just going to be another constant, so we're just going to rename it k because it's a different constant than c is. So we have the absolute value of 1 plus y equals e to the ln absolute value of x plus c. And so then you simplify that down into 1 plus y equals k times the absolute value of x. Now we're in simplest form. And so you want to go ahead and plug in the point that the problem originally gave you, negative 1, 1. So we have 1 plus 1 equals k times the absolute value of negative 1. So that's just 2 equals k times 1, which is just 2 equals k. So that automatically gives you your constant right there, and you can plug that back into the original equation. So you get 1 plus y equals 2 times the absolute value of x. And then you simplify that by moving the 1 over, and you get y equals 2 times the absolute value of x minus 1. And so they also ask you to state the domain in this problem, and we know that that is x is less than 0, because first of all, they say x cannot not equal 0 in the given part of the problem. And also, if you took a look at our slope field from part A, you can see that both sides dip down and do not cross the y-axis when x equals 0. So we know that it's not going to go over to the positive side since we're just looking at the left-hand side. So that's why our domain is x is less than 0. And then another way you could write that is y equals negative 2x minus 1 when x is less than 0, because if x is always negative because we have that domain, then we can basically bring those absolute value bars out and just put a negative sign. As far as grading goes for this problem, it's pretty straightforward. It's just points per steps. So the first point you're going to get is for separating your variables. Then you get 2 for taking the antiderivatives correctly. Then 1 more for having the constant of integration. Then 1 more for using your initial condition, which is your derivative and your point that they give you. And then 1 point for solving for y correctly. And then 1 point for having the correct domain. And one thing that I forgot to say in the last part was, in this part of the problem, the reason we can drop those absolute value bars is because this constant is going to absorb the negative sign if it really is negative. So that's the explanation of this problem. If you guys still need more help with slope fields, here are some other problems you can look at. The AP Calc AB exam from 2014, number 6, part C is really helpful. 2004, number 5, I really like that problem. It's very similar to this one. It's extremely helpful if you're still having trouble with slope fields. And then 2005, number 6, is just an all-around good problem, not just with slope fields, but also with other topics. Thanks for watching, and I hope this video helped you. And once again, as I always say in all of my video projects, Mr. Farrar, if you're watching this back from my letter of recommendation, please assume I was your favorite student.